So in this lecture, we will review vector calculus. It's impossible to separate vectorial calculus from the study of aerodynamics. So let's review some of the most important fundamental concepts regarding that. Okay, let's start with a couple of definitions that we use very often. First of all, let's define some quantities here. Okay, so what's a scalar? First of all, let's define what's a scalar. Okay, a scalar is nothing else than, or scalars is quantities that specify only magnitude. An example of that is, one example of this is speed. Okay, so speed is just a value, doesn't have directions. So you say the speed was equal to 10 meters per second, as for an example, or it's in the v direction, y direction, then you could say your speed is equal to, let's say, 10 feet per second, right? It's just a magnitude. You have no clue what the direction is. It's just a pure magnitude. That's a scalar. Then a vector, what are vectors? Vectors are quantities that have magnitude and direction. Okay. An example of a vector is, let's say, velocity, right? So velocity can be a vector. Okay, I use this arrow at the this dash below this to reference a vector. Many times, many authors use the arrow on the top of it. Either way is correct. So you can have velocity in the u direction, I, plus a velocity in the y direction by j, plus a velocity in the z direction, k. So this is a vector. Okay. Now, let's define bound vectors. What are bound vectors? These are quantities that have magnitude, direction, and a point of origin. They have magnitude, direction, and a point of origin. One example of this is the position vector. The position vector is a vector that's fixed in time. That's fixed in space, sorry. Let's say x, y, and z. And now I have a vector r. This is a position vector. And you can see that this position vector is something like this. So it has all components in the x, y, and z plane. Okay, that's one example. When we work with vector algebra, we can have vectors and we can add vectors. Okay, so let's call this vector algebra. Um, the first property of vector algebra is that we can add or subtract vectors. So if I have a vector A, I have a vector B. This is the same, doesn't matter the order I add them, um, it will still be valid. If I have subtraction, I cannot necessarily swap them, obviously, right? And I'm sorry, this is vector A. And this will give me a new vector C, and let's call this a new vector D. Okay? How we add vectors? As a quick example, let's suppose I have a vector 3i plus 4k, and I have a vector B that would be minus 3j plus 7k. Um, so if I'm going to add the vectors, there are two ways to do this. First, I can just add all the components of j. I like to do it like this. I like to write them at 4. When I add vectors especially, 4, 0, because I don't have a k. And then I don't have a I, so it's a 0. This is minus 3, this is 7. So when I add these vectors, I'm adding each one of the components, um, each one of the components of the vector. So this will give you 3 plus 0, 3, 4 plus minus negative 3 gives you 1, 0 plus 7 gives you 7. So that means that your new vector here is 3 times I plus j plus 7 times k. That would be the summation of the vector. If I am subtracting the vector, then I can simply subtract the vector as follows. Minus 0, minus 3, 7. And when I have a minus sign, the first term remains the same. Okay, I can change that to plus, but then each one of the components become minus. So this becomes plus. I multiply them with a minus 1. You see, minus 0 is 0, minus minus become plus, minus plus becomes negative. So now I just subtract, I just add this term. So this gives you 3, 7, and minus 7. So the subtraction of this vector gives me 3 plus 7j minus 7k. Okay? Another thing that's very common, and we use this, is called the unit vector. The idea of the unit vector is just that comes from the word unity, right? It's unit. So if I take the magnitude of this vector, it would give me 1. So it's a vector whose magnitude is 1. Okay, how do I find the unit vector? Well, the unit vector is found as follows. So let's suppose I have a unit vector. I want the unit vector of A. So I will have my vector A, and I would take the norm of A. The norm of A is nothing else than each one of the terms component squared. Okay, so for this example, I had 3 and 4. So the unit vector then would be, I have 3i, this is an example, okay? Just put the examples here, is 3i plus 4j, that's the unit vector. And then this all will be the square root of 3 squared plus 4 squared and plus 0 squared. So this gives you 16, 9, this is 25, the square root of 25 is 5. So this whole thing gives you 3i plus 4j divided by 5. Okay? Or if you want to write it down in this particular vector is a unit vector. Okay? And it acts in this unit, a vector acts in the direction of my vector A. So if I have this vector, that this vector goes in this direction, this is my vector A, right, that has these components, then my unit vector is the vector in the same direction, is EA. But if I take, I like to personally call, let me just delete this, I like to call this with hats to distinguish this. Sorry, just fix that in your notes. I like to call it hats because for unit vectors, that's what I like to do it. Okay, so you can look at it. If I'm going to find the absolute value, if I'm going to find the norm of this will actually give you 1, and you can show that. You can show that to yourself. So what is a zero vector? This is another quantity. It's kind of trivial. The zero vector is just that. It's a vector where all the components are 0. Okay, so is a vector if all the components are 0. The vector has no magnitude, and if it doesn't have any magnitude, I cannot tell what direction it has. So it has undefined direction as well. Okay. Then a couple of more things about vectors that is very, very useful is the dot product or the scalar product. Okay, or known as dot product. Okay, again, this should be more of just a review. But anyways, if I have a vector A and I have another vector B, then I take the dot product of this, the projection will give me this dot product. This is the projection that we get. Okay, so dot product is nothing else, is the orthogonal projection of A along the direction of B. Okay, so how do we find this? Well, then it becomes A dot B will be the magnitude of A, the magnitude of B times, or just write it correctly, it's the magnitude of A, the magnitude of B times cosine of theta. And the result, when you do a dot product, you get a scalar. This is nothing else than a scalar. Okay, so if I did the dot product for this particular vectors, just to give that as an example, so the dot product would be nothing else than for these two vectors, A dot B, it is basically taking each one of the components and multiplying by itself and adding them up. So all the i's together, this is 3 times 0, I don't have nothing here, plus 4 times minus 3, because I have a minus 3 there, plus 0 times 7, because I don't have a k there, and that gives you minus 12. Okay, so that is the dot product. That's a scalar of that. And so that is what the dot product tells you. There are a couple of properties of dot products that are important, and we use them very often, and they will become very handy as we move along in the course. When you take the dot product of two vectors and gives you 0, then what you're really saying is that the vector A is at 90 degrees for vector B. In other words, my vector A and my vector B will be exactly at 90 degrees. Okay. However, if I say my vector A dot product vector B is equal to 1, then basically what I am saying is these two vectors are parallel to each other. Okay. And what I mean by that is I am saying I got my vector A, and vector B goes exactly in the same direction, but is shifted in space. So they are parallel to each other. Okay. Now, the other component that we use very often is called the cross product or the vector product. Known as cross product. Okay. So a cross product is nothing else than if you use the right-hand rule. So if I have my vector B and I have my vector A, and I am going to cross A times B using the right-hand rule, your thumb goes in this direction, so your thumb goes in the upper direction. So therefore, this will be your C vector. Okay. So this will give you nothing else than A cross B produces a vector C that's 90 degrees to these surfaces. Okay, to the surface that's enclosed by the AB vector, A and B vectors. One example of this, if we use the same vectors that we have been working with, and we are working with Cartesian coordinates, then this gives you I, J, and K, and your vector A was 3 and 4, so I put 3 and 4 and 0. Then you get here minus 3 and 7, so this is 0, minus 3 and 7. So these are the vectors I have. How do you solve this cross product? You have to do it in parts. Okay, so doing these vectors, the solution is very easy. The first thing I want to do in the vector is I put here, the easy way to do it is you put plus, minus, plus. Then you start with the first component, okay? And then you say the whole thing will be I, okay? And it's plus, so I put a plus. Then you basically eliminate this column and this row, and you cross product. You do 1, and then you do 2. Okay? One and 2. So you do 4 times 7 minus 3 times 0. Okay? Then you repeat the whole thing again. But now we move to the next one. Okay? So we say this is plus, minus, plus. Now we work with J. And then this will be minus. So this is minus J. And we eliminate this column and this row. And you end up with these two. So now you cross product these. 3 times 7 minus 0 times 0. Okay, and then you do the last one. Do the same thing, plus, minus, plus. Now you start with this one, has a plus, so it's plus k. You eliminate this row and this column, and you end up with 3 minus 3 minus 0 times 4. Okay, so the whole answer is the summation of all these three. So this gives you 28. So 28 times I. This gives you minus 21 times j. This gives you minus 9 times k. So this is the solution to this cross product. Again, it's supposed to be more of a review. Okay, so we can also use the cross product to determine the area of a parallelogram. But I'll let you review. I will let you review that. Okay, there are many other neat properties that we can apply and we can complicate, and we will leave some of the stuff for your homework. First of all, I can have the dot product of the cross product of A, B, and C is actually the same as the cross product of B taking the dot product of C. That's a neat property that vectors have. Also, you can, another interesting property is that if I want to take the cross product of the cross product of all these vectors, sometimes it's very, very useful to just simplify all of these using the following properties. And trust me, it's a huge time saver. Okay? Times, this is a scalar, it's a dot product times b, minus a dot b is a dot product, so it's a scalar. So then you can just show that this whole thing is equal to this. And it becomes very, very, very easy to solve these problems. Okay? So another thing that we can keep in mind that we use also is in the coordinate system that we work with. Okay? So let's work with the coordinate system. Okay, so if I'm working in the Cartesian coordinate system, the Cartesian coordinate system, let's call E1 I, let's call E2 J, let's call E3, let's call it K. Now, if you're working in the cylindrical coordinate system, Cartesian, and the cylindrical is very popular that we use in fluid mechanics or aerodynamics, is because sometimes the fluid's in rotation, it makes more sense to have a cylindrical or spherical coordinate system. In this sense, your unit vectors work a little bit different because it's in the radius, in the rotation theta, and in the annual direction z. As for an example, this one is easy. So you can just say that your E1 is actually equal to K, is equal to J. I'm sorry, I. Your E2 is actually equal to J. Your E3 is actually equal to K. In this coordinate system, it works a little bit different. So if I have this vector and and I have a rotation here. So what I would do is what's going on in this direction is my ER, that is my E1. This rotation, the vector in the theta direction, it is E theta, and that would be my E2. And then everything perpendicular to this axis would be my EZ. That would be E3. Okay? So those two coordinate systems end up being very, very important. And we will talk about them as we move along. Another thing, why we learned all this is because in vector calculus, we can represent the plane area as a vector. And that becomes very useful, especially when we are working with vector integrals. Okay? Plane area representation. Well, it's a plane area representation. Think about, you got a plane, okay? This is a plane and then you have some reference here, some piece of area, okay? And so we're going to call this C. C will mean the contour of a small portion. And in this contour, we have, let's put this in a different color. We have a vector that's at 90 degrees, and let's call that unit vector n. Okay, so this is the unit normal. Unit normal to the surface. And then the enclosed area, let's call this the S. S will be the area inside the contour. Then what I can use is, you can use your right-hand rule to show that your vector S is equal to S times your vector N. Okay, this is your right-hand rule. We call this RHR many, many times. And you're going to see that approximation throughout this course. Okay, so now that we have that, many times we have vectors that are, there are different names of those names. So for instance, we can have a polar vector. A polar vector is one that represents properties that are perpendicular to the direction to the vector. So for an example, the previous case I had, a polar vector could be S. That is the, so the area vector is a polar vector. Okay. So polar vectors are nothing else than they represent properties perpendicular to the direction of the vector. Okay, so those are polar vectors. Now, in most of the problems that we solve, we are very much used to what we call the axial vectors. Axial vectors are nothing else like velocity, like force, right? Because they are a property represent something in the direction of the vector. So this is, as an example, is the velocity. and force. And these basically represent properties in the direction of the vector. Okay. Let me ask you a question. So, what do you think would be the angular velocity? As for an example, the angular velocity is a direction, is an axial vector or a polar vector? Well, let's see. So if I have a particle, right, and a particle is rotating in this direction, right, and that's creating a flow actually in this direction. So I am producing an angular velocity, but angular velocity is about this 90-degree surface. So this, in this particular case, because I am rotating about the surface, and you're producing a vector that represents, so it's a representation of what's happening here, then this will be a polar vector. Okay. So let's suppose we have a rigid body rotation. What is a rigid body rotation? So let's suppose I have an arbitrary body, okay? In that body, I have, let's suppose, a coordinate system, okay? So in this coordinate system, I have something in this direction. So everything is happening in this direction, okay? And so this coordinate system, what's happening is from this point to here, you are rotating about this and you're creating a rotation. And this rotation is producing a path that goes around this, goes in this direction like this. So I have a point here and I have my origin somewhere there. So what I have is from here to here, this is a position vector. Let's call this R, okay? And then this is actually my, so let me see what I can do here. Just give me a moment. I use orange. So in this direction, this is ER. Then if I go in this direction will be E omega because it's in the perpendicular direction. And this is rotating in this direction. Because it's rotating in this direction, then we're going to call it E theta. It's a rotation, a particle that's rotating like this. This body is rotating with a fixed point here, and then you have a point that's actually rotating over and over and over again. So for this particular case, you can show that your velocity is equal to your rotation speed times the cross product times your angular velocity times your position vector. I am not going to give a proof for this, but this is also very, 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 very important, and we use this. Okay, so let's move on now. Let's talk a little bit about velocity and displacements. Okay. Okay, so let's suppose I have a stream, okay, and I have a particle there, okay, and that particle is going at the velocity v, and I also then I have a small delta s, okay, and this is my path s, okay. This is actually parallel to the surface here. So d of s is nothing else than the increment of the displacement vector. And then if I can write this, I can write this as ds is as es, right? Where es will be nothing else than the vector in this direction. Um, and also know that the velocity is nothing else than, if this is the velocity, then this will be the unit vector, right? So what you know is from physics that your velocity is nothing else than dt. If I take the derivative of this gives you nothing else than ds dt es. Note that you could make the argument and say I have something missing here. Maybe I should also put ds d as e dt, but this is a unit vector, so this is going to go to 0. Okay, so this whole term, goes to 0. I don't have that term. Okay, so this whole thing then is nothing else than dds. This is the velocity times, okay, just so this is velocity, okay, and now note that your velocity has to be in terms of v, okay. So in other words, this is the same thing as d as dt times ev, okay. Okay, that's your velocity. That's the relationship with both of them. So if we go ahead and relate these to quantities I just gave you in the previous page, and I showed you that ds is actually EV, and I also said that ds is ds times es, and you can see this from here, right? Because this is equal to es, but this is equal to EV, and this my coefficients are basically identically the same. So what I can conclude from here is that EV is actually equal to ES. Okay. Uh, okay. Okay. So a couple of more definitions here. Let's work with fields. What are the fields? And we talk about fields all the time in aerodynamics. Fields are nothing else, points of origin, points, um, they're nothing but points of a given region and values in that particular regions, okay, functions of that region. So fields are points of a given region and values of a function in that region. Okay, so for instance, if a function is a scalar, what do you expect that it will produce? Let's suppose a function is a scalar. What would you get? Very good. You expect to get a scalar field. That's going to produce a scalar field because it's a scalar. Okay, so you're going to get a whole bunch of points. Now, what if a function is a vector? What do you expect? Very good. You will get a vector field. Okay, because scalars produce scalars, vectors produce vectors. Okay, we're going to do a lot of examples with that as we move on. Another thing that you have to keep in mind when we talk about this unsteady flow, uh, especially unsteady flow, when I talk about steady field, I am talking that doesn't matter whatever you're working with, it is going to be something is going to be a function of time. Okay, this function can be scalar, can be a vector. Okay, as an example of this is maybe I have the speed, and I can say my speed is a function x, y, z, and time. So I can say my speed is x, x cosine times, or just say 4 cosine t. Okay, that's your speed. Now I can say is a velocity. Okay, it could be velocity if this becomes 4 cosine t I plus x times j, where I can say maybe x is another function of time. Okay, so that's how we actually work with this type of this is unsteady field. And obviously, if I'm working with a steady field or a stationary field, then you can expect it's not, right? It's a stationary or steady. We mean that is time independent. Okay. Okay. So another thing that we also have fields, we call something called field lines. This is what we spoke in the last topic, like streamlines as for example. Okay. Field lines are nothing else than lines tangent to a vector quantity. At each point along the line. Okay. And so one example of this is the streamlines, right? That we talked about that last time, because streamlines are lines that are tangent to velocity. To the velocity vector of each point along the line. Okay. If you want to construct the field lines, one way to do that is, for instance, let's suppose your vector A is a function of your position r and time t. Then let's suppose, okay, this is this position right here. From this point, I'm going to have a position r, okay, and this point, this is at t1, let's say. Now, there's a small vector ds that's crossing that line here that passes through this. So what you can show here is, sorry, you have a position vector that's actually going in this direction in this point. This point right here, there's a, just give me a second. Let me redraw this. So let's suppose from here, I have a position vector. Just need to get it tangent, okay? So with the position vector, I'm going to have this other vector here, that is your ds, your small segment where this moves. Okay, so this is a position vector. And what you can show is that your ds is actually parallel to r. Okay, and if you just remember the vectors that are parallel to r, how we can, if you go a couple of slides back, you remember if I take the dot product and the dot product is equal to 0, I can show this. Also, there's other neat properties that we can show, that this is also true if my vector ds, okay, was actually equal to cross times a is equal to 0. Okay, so this cross product could be there's a velocity, as for an example, and you can actually show that your stream can be derived by using this cross v that would give you the 0 vector. And you can do this calculation and you can show that you actually, by doing that, you get the equation that we derived in our previous class that actually shows that this was equal to this. Okay, this equation that we derived in the previous class, actually comes as a consequence of this property. Okay, because those are field lines, what we are talking about. So this will conclude the first part of the theory. Let's stop. This is a good stopping point, and we will do some examples and we come back to do some more problems. We'll continue the theory.